So we're going to look at another effect that is caused by application of the Bernoulli equation. It's called the Venturi effect, and it allows you to measure flow speed, particularly in a pipe, without inserting a probe. So if we know we can measure flow speed by inserting a pitot tube, you did that in the quiz yesterday, and you also know that there are other devices you can put into a flow to measure the flow speed, various different types. Anemometers work usually by measuring cooling on a wire. But at any rate, sometimes you want to do that without inserting an actual object into the flow. So here's another way to do it. You can cause the flow channel to get narrower, changing the cross-sectional area, and that's going to cause, based on the Bernoulli equation, we know that's going to cause a pressure drop, because of course when you close off that cross-sectional area and make it smaller, the same amount of mass has to flow through the pipe at every location through mass conservation if this is incompressible flow, which we'll assume that it is, in which case the velocity at this narrower portion is going to have to be faster. And so that's going to cause a pressure drop. And by looking at the pressure drop between these two, if we know the two areas, we can calculate how fast the flow is moving at either of the two locations. So in order to do that, we're going to imagine I'm trying to find V1 here. I don't know it. It's there, and I want to measure it. So I attach the pipe to this Venturi meter, and I'm going to measure these two pressures to figure out what V1 is. So the Venturi equation, of course, is here. I noticed today in class that a few of you didn't really start with the fundamental equation. You started with shorter versions of it, specific to, you hoped, specific problems. I would definitely encourage you to go to the original equation as often as possible. It's just, it's easy to eliminate stuff if you don't need it, but if you don't include it to begin with, it's sometimes hard to get it back. At any rate, this is the Bernoulli equation. We know that this value here has to be constant. So this value at point 1 is going to equal the same constant at point 2, so they're going to equal each other. There is no change in height in this problem. Z1 is equal to Z2 quite clearly from the picture. There's really no height change in the flow, so those are going to cancel. So we can rewrite this in terms of the two pressures. P1 minus P2 is equal to rho times V2 squared minus V1 squared over 2, where I've just pulled the velocities to one side, the pressures to the other. Notice the sign change such that I have P1 minus T2 and V2 squared minus V1 squared over there. Now I'm going to apply mass conservation. Again, I'm going to write the whole equation down. That's mass flow at point 1. This is mass flow at point 2. There's no difference in density because it's incompressible flow. So we're going to say none of that. And therefore, we can just rewrite V2 in terms of V1. V2 is equal to V1 A1 over A2. So that's going to allow me to eliminate V2 from this equation. So I'm going to plug this V1 into there, and that will give me an equation with only the pressure difference, the thing I'm going to measure, and the velocity that I'm after. So I'll go ahead and write that. So I have P1 minus P2, which I'm going to measure, is equal to rho over 2 times V2 squared, but I'm going to replace V2 squared with my V1 A1 over A2. I'm going to square that minus V1 squared. Oh, there it's all, and then that's that. So there's my my new equation for P1 minus P2, and then I can solve that for V1 squared. For V1 squared. So I'll pull V1 squared out. So I'll have P1 minus P2 rho over 2 V1 squared times A1 over A2 squared minus 1. And then I'll push everything over to the other side to solve for V1 squared. V1 squared is equal to P1 minus P2 divided by rho over 2 times A1 over A2 squared minus 1. I can obviously multiply up and down by 2, so I get V1 squared equal to 2 P1 minus P2 divided by rho A1 over A2 squared minus 1. All right, and finally, of course, I'm just going to take the square root of that. I get square root V1 is equal to the square root of 2 P1 minus P2 divided by rho A1 over A2 squared minus 1. And that's my velocity. So I can measure my velocity. Oops, you can't quite see it. I can measure my velocity as a function of this measured pressure difference in the Venturi meter. And then I can calculate V1. And I don't actually have to know either P1 or P2. I only have to know the pressure difference between P1 and P2 in order to get my calculation for velocity.